More details later in the video. From the first idea of a quantum computer in 1980 to today, there's been a huge growth in the quantum computing industry, especially in the last 10 years, with dozens of companies and startups spending hundreds of millions of dollars in a race to build the world's best quantum computers.
For most of us, it's quite hard to get our heads around the world of quantum computing, and a lot of information about it glosses over important details. This video aims to clear all this up, and if you watch the whole thing, you'll have a very good overview of the different kinds of quantum computing, how they work, and why so many people are investing in the quantum computing industry. This is the map of quantum computing.
Quantum computers solve problems in a different way to the computers we're familiar with, which, from now on, I'll be referring to as classical computers. Quantum computers have certain advantages over normal computers for certain problems, which comes from their ability to be in a huge number of states at the same time, whereas classical computers can only be in one state at a time. To understand this, and to understand how quantum computers work, you need to understand three things: superposition, entanglement, and interference. The building blocks of a classical computer are called bits, and the building blocks of a quantum computer are called quantum bits, or qubits for short, and they work in fundamentally different ways. A classical bit is kind of like a switch that can either be a 0 or a 1, which you're probably already familiar with as binary or binary information. When we measure a bit, we just get back the state that it's currently in. But we'll see this isn't true of qubits. A qubit is more complicated. For a useful visualization, you can think of them as an arrow pointing in 3D space. If they point up, they're in the 0 state, and if they point down, they're in the 1 state, just like a classical bit. But they also have the option to be in a thing called a superposition state, which is when the arrow points in any other direction. This superposition state is a combination state of 0 and 1. Now, when you measure a qubit, the output it gives will still end up being either a 0 or a 1, but which one you get depends on a probability which is set by the direction of the arrow. If the arrow is pointing more upwards, you're more likely to get back a 0 than a 1, and if it's pointing downwards, you're more likely to get a 1 than a 0. And if it's exactly on the equator, you'll get either state with a 50% probability. So that's the effect of superposition explained. Now we'll move on to entanglement. In a classical computer, the bits are independent from each other. The state of one bit is not influenced by the state of any of the other bits. But in quantum computers, the qubits can be entangled with each other, which means they become part of one large quantum state together. For an example, let's look at two qubits which are each in different superposition states, but aren't entangled yet. You can see the probabilities next to them, and these probabilities are currently independent of each other. But when we entangle them, we have to throw away those independent probabilities and calculate a probability distribution of all the possible states we can get out, either 0, 0, 0, 1, 1, 0, or 1, 1. The important point here is because the qubits are entangled, if you change the direction of the arrow on one qubit, it changes the probability distribution for the whole system. So the qubits are no longer independent of each other. They are all part of the same large state. And this is true no matter how many qubits you have. You'll also note that for one qubit, you've got a probability distribution over 2 states. For 2 qubits, you've got a probability distribution over 4 states. For 3 qubits, you've got a distribution over 8 states. And this keeps on doubling each time you add another qubit. In general, a quantum computer of n qubits can be in a combination of 2 to the power of n states. So I'd say that this is the core difference between classical computers and quantum computers. Classical computers can be in any state you want, but can only be in one state at a time. Whereas quantum computers can be in a superposition of all of those states at the same time.
But you may wonder how being in this superposition state can be useful in a computer. Well, for that we need the final component, interference.
To explain the effect of interference, we need to go back and look at my picture of a qubit, technically called a Bloch sphere. Now, a qubit doesn't actually look like this. This is just a really nice way of visualizing the state of a qubit. In reality, the state of a qubit is described by a more abstract entity known as a quantum wave function. Wave functions are the fundamental mathematical description of everything in quantum mechanics, which I've described in more detail in a previous video. When you've got many qubits entangled together, all of their wave functions are added together into an overall wave function describing the state of the quantum computer. This adding together of wave functions is the interference, because just like with, say, ripples of water, when we add waves together, they can constructively interfere and add together to make a bigger wave, or destructively interfere to cancel each other out. The overall wave function of the quantum computer is what sets the different probabilities of the different states. And by changing the states of different qubits, we can change the probabilities that different states will come out when we measure the quantum computer. Remember that even though the quantum computer can be in a superposition of millions of states at the same time, when we measure it, we only get a single state out. So when you're using a quantum computer to solve a computation problem, you need to use constructive interference to increase the probability of the correct answer, and use destructive interference to decrease the probabilities of the incorrect answers, so that when you measure it, the correct answer will come out.
Now, how you do this is in the realm of quantum algorithms. And the whole motivation behind quantum computers is that theoretically there are a bunch of problems that you can solve on a quantum computer that are thought to be intractable on classical computers. So let's take a look at them.
There are many quantum algorithms, too many to describe in this video, so we'll just focus on the most famous and historically important, Shor's algorithm. If you've got two large numbers and you multiply them together, there's a fast, efficient classical algorithm for finding the answer. However, if you start with the answer and ask what are the original numbers that multiply together to make this number, it's a lot more difficult. This is known as factorization, and these numbers are called factors. And the reason finding them is so hard is because the search space of possible factors is so large. And there's no efficient classical algorithm for finding the factors of large numbers. For this reason, we use this mathematical property for internet encryption, secure websites, emails, and bank accounts. If you know these factors, you can easily decrypt and view the information. But if you don't, you need to work them out first, which is intractable on the world's most powerful computers. Which is why in 1994, when Peter Shor published a fast quantum algorithm that can efficiently find the factors of large integers, it caused quite the stir. This is the moment that a lot of people started to take the idea of quantum computing seriously, because it was the first application to a real-world problem with potentially huge real-world security implications.
But when I say a fast quantum algorithm, how fast? And how much faster than a classical computer would it be? Well, to answer these questions, we need to take a little detour into the world of quantum complexity theory.
Quantum complexity theory is a subfield for the world of computational complexity theory, which deals with the categorization of algorithms, sorting them into bins according to how well they run on computers. The categorization is based on how much harder it is to solve a problem as the problem gets larger. Here, any problem inside the P box is easy to solve with a classical computer. But anything outside it means we don't have an efficient classical algorithm to solve them, and factoring large numbers is one of these. But there's one box here, BQP, which is efficient for a quantum computer but not a classical computer, and these are the problems that quantum computers will be better than classical computers at solving. As I said, complexity theory looks at how difficult it is to solve a problem as the problem gets larger. So if you factorize a number with 8 digits, then you add another digit on, how much harder is it to factor the new number compared to the old one? Is it twice as hard or exponentially harder? And what's the trend as you add more and more digits? This is called its complexity or scaling, and for factorization it's exponential. These exponential problems are the problems that really screw you over as the problems get bigger. And in the world of computer science, you can win respect and renown if you find a better algorithm to solve these hardest problems. One example of this was Shor's algorithm, which took advantage of the special features of quantum computers to create an algorithm that could solve integer factorization with a scaling much better than the best classical algorithm. The best classical algorithm is exponential, whereas Shor's algorithm is polynomial, which is a huge deal in the world of complexity theory and computer science in general because it turns an intractable problem into a problem that can be solved. Solved, that is, if you have a working quantum computer, which is what people are working on building. But you don't need to worry about the security of your bank account yet, because today's quantum computers are not able to run Shor's algorithm on large numbers yet. I've estimated that they'd need about 1 million qubits to do so, but so far the most advanced universal quantum computers have around 100. Also, people are working on what's known as post-quantum encryption schemes, which don't use integer factorization. And another technology from the world of quantum physics can help here too, a cryptographic scheme known as quantum cryptography. So that was a look at just one quantum algorithm, but there are many more, each with different levels of speed up. Another notable example is Grover's algorithm, which can search unstructured lists of data faster than the best classical algorithm. But I should be careful here to make sure I don't mischaracterize classical computers. They are very versatile devices, and there's nothing to say that someone may find a very clever classical algorithm that could solve the hardest problems like integer factorization more efficiently. People think it's very unlikely, but it's not ruled out. Also, there are problems that we can prove are impossible to solve on classical computers, called non-computable problems, like the halting problem. But these are also impossible to solve on a quantum computer. So computationally, classical computers and quantum computers are equivalent to each other. The differences all come from the algorithms that they can run. You can even simulate a quantum computer on a classical computer, and vice versa. But simulating a quantum computer on a classical computer gets exponentially harder to do the more qubits you're trying to simulate. This is because classical computers struggle to simulate quantum systems. But because quantum computers are already quantum systems, they don't have this problem, which brings me to my favourite application of quantum computers, quantum simulation. Quantum simulation is simulating things like chemical reactions or how electrons behave in different materials with a computer. Here, quantum computers also have an exponential speed up over classical computers because classical computers really struggle to simulate quantum systems. Now, I've made a whole other video about quantum simulation which you can watch here, but basically, simulating quantum systems with as few as 30 particles is difficult even on the world's most powerful supercomputers. We also can't do this on quantum computers yet, but as they mature, a main goal is to be able to simulate larger and larger quantum systems. These include areas like the behavior of exotic materials at low temperatures, like understanding what makes some materials superconduct, or studying important chemical reactions to improve their efficiency. One example aims to produce fertilizer in a way that emits way less carbon dioxide, as fertilizer production contributes to about 2% of global carbon emissions. Other potential applications of quantum simulation include improving solar panels, improving batteries, developing new drugs or chemicals, or materials for aerospace. In general, quantum simulation would mean that we'd be able to rapidly prototype many different materials inside a quantum computer and test all of their physical parameters, instead of having to physically make them and test them in a lab, which is a much more laborious and expensive process. This could be a lot faster and save a huge amount of time and money. But it's worth reiterating that all of these are potential applications of quantum computers because we don't have any quantum computers that can solve real-world problems better than our normal computers yet. But these are the kinds of problems that quantum computers would be well suited to. Other applications outside of quantum simulation are optimization problems, machine learning and AI, financial modeling, weather forecasting and climate change, which I'll be honest, I don't really understand how that would work. And finally, cybersecurity, which I think just boils down to Shor's algorithm, which I've already described.
Now, we need to be a little careful about the potential for hype here, as a lot of the claims of what quantum computers will be good for come from people who are actively raising money to build them. So it makes sense for them to piggyback on topical subjects in their pitches. But my take on this is that historically, when a new technology has come along, people of the time aren't generally the best at being able to tell what it's going to be used for. For example, the people who first invented the computers never dreamed of the internet and all of the things on it. And this is likely to be the same for quantum computers. So for me, the application I can really understand is quantum simulation, and that's why I've focused on that in this video. Anyway, so far I've described how quantum computers work and what problems they can solve. But most of what I've talked about so far is theoretical. And for the rest of the video, I want to focus on reality. How are people actually building quantum computers, and what can they actually do? Now, it's worth mentioning here that some physicists are skeptical that it will ever be possible to build a quantum computer at the scale needed to solve real-world problems. But the people working on all of the following certainly don't agree. Now, quantum computing is often portrayed as if it's a single thing, but inside the world of quantum computers, there's a large range of approaches to turning different kinds of quantum systems into quantum computers. And there's two layers of nuance I need to talk about.
First of all are the models of quantum computing, the overall approach to manipulating a collection of qubits. And then there's the physical implementations, the actual quantum objects you build your qubits from, like a superconducting loop or individual atoms or photons. We'll start with the models of quantum computing.
It's interesting that there are different models of quantum computing because this isn't something we see with classical computers.
Practically all the computers we use today work in the same way. They have a bunch of bits holding the binary information of ones and zeros, and we can do operations on those bits using logical gates, which are basically simple operations that flip a bit, called a NOT gate, or compare bits, like, for example, giving you a 1 if both input bits are 0, or a 0 if they're anything else. This is called a NOR gate. Interestingly, you can build a full general-purpose computer from just bits and NOR gates. In quantum computing, there's a similar model to this called the circuit model or gate model, which is the most popular approach and the most understood model in quantum computing. In the circuit model, you have your collection of qubits which are entangled with each other, and then you have a bunch of gates which can perform operations on small numbers of these qubits, which change the state of the qubits without measuring them. A quantum algorithm is built from a sequence of gates applied to the qubits in a certain order, and then a measurement at the end, which is where you get your final state and is hopefully the answer to the problem you're trying to solve. Simplistically, you can think of these gates as operations on the qubits that rotate the arrows to point in different directions. And these operations change the probability of the final state of each qubit when it's finally measured.